Okay, almost right in time. There's a small change in the schedule, and now the first talk now is going to be the one which was expected to be last. So Jordi Blasco will be talking now, and the last talk today will be from Ingrid Bárcena, which was scheduled for tomorrow, but will be today the last time. So now Jordi, our beloved great leader, is going to talk us about cluster provisioning. I know that it will be very interesting, so we'll keep up. Even without coffee, we'll be able to stay here.
Thank you. So this talk, just to summarize the work that I have been doing maybe last 2 or 3 months in HPCNow regarding cluster provisioning as a part of HPCNow Cluster Manager. So this is the agenda. It's quite intensive session. So I will try to speed up some slides because I know that all of you are pretty aware about many of the technologies that I'm going to mention here. So this is the agenda. I'm going to explain a bit what motivates us to go even further in terms of technology, to accelerate and to get more flexibility in the cluster provisioning. I'm going to summarize a little bit what the deployment provisioning means, what kind of technology is available now in terms of image provisioning, and then improvements that we have done in terms of diskless provisioning, and finally some conclusions about that. So main motivation is flexibility. So sometimes you need to be able to accommodate user requirements that have maybe different kind of OS requirements or different even kind of workloads that needs to be managed by Docker, for example, or many other stuff. You want something that can switch from a cluster or traditional cluster to something that can be Docker Swarm-based or OpenStack or whatever you can imagine. You could use exactly the same infrastructure. So I want something that it's really resilient, that it doesn't depend on rely on a specific hardware that if it crash, the whole thing goes down and it's impossible to work with. As well, I want the same technology, exactly the same technology that can be suitable for one node to thousands of them. I don't want to switch the technology every time I have to deal with a different customer or different scenario. So this is actually really good because in terms of end user support, you only need to worry about the same technology, not many of them, or several of them. And also online changes. I want to be able to perform online changes without the need of rebooting the system in order to be able to apply that thing. This usually, it's quite challenging if you want to apply on top of regular provisioning DevOps mechanisms or DevOps methodology. Because usually in DevOps, you have a scripted way to reproduce the same thing, but usually at the end, usually you need to restart the system. We are going to review that thing a little bit later. And then fast provisioning. So that thing needs to be happening really quickly. And so we are talking about minutes to provision a larger scale, or relatively larger scale cluster. And again, ideally should be DevOps and continuous integration friendly. So deployment-based provisioning. So this is more or less a standard pipeline. So the system boots through, usually through PXE. Then you have an unattended installation. It depends on the Linux distribution that you're using. So Kickstart or AutoJust or whatever. And then the OS user, it's installed in the local disk. After that, you reboot the system, and if you want to perform any changes online, you need to revisit the way that you describe the image, or use a config manager to propagate the changes in the cluster. So, and this means that usually you need to implement or to take into account several agents, one per compute node, okay? So pros, well, it's the good is that it's pretty flexible, it's really easy to understand, and it's DevOps friendly and continuous integration friendly. The bad, okay, so local disks are not usually very, very reliable, and if you want that thing to be reliable, you need write one at least, and it starts to become expensive, right? So if you think about investing money in local disk in all the compute nodes, as long as you have more and more compute nodes, you have to spend more and more money, okay? So unless you want to set up a different use case on top of that thing, like a BCFS on demand that somebody have talked previously, so it makes no sense to use, to go to this direction unless you have a real reward on that thing. And in addition to that, you need long period of time to deploy a large cluster, because it's usually RPM-based or Debian package-based. It's serial, and you can parallelize that thing little bit, but usually you download all the packages per node basis, and then you extract the files from the packages. So it's usually a tedious and really, really slow way to provision a cluster. And at the same time, it's not easy to apply changes online. So you have mechanisms like parallel distributed shell or cluster shell or whatever, but it requires manual intervention. Okay, you can set up a config manager on top of that thing, to propagate the changes in the cluster, but again, those changes are not going to be applied immediately. So you need to take into account that this is, well, depends on the config manager, but you need to take into account that those changes, it's going to be performed later, okay? You don't know when it's going to happen. So it's not something that's going to happen instantly. So then, because it's local disk, you have a huge risk on cluster inconsistency. So you have a disk failure, you replace that thing, you reimage that thing, but if you have already performed any change online, this node is not going to grab that thing, unless you're using a DevOps methodology, okay? So image-based provisioning allows you to accelerate that thing a little bit. I'm not going to explain that thing in detail, but basically it means that you extract an OS image and you deploy that thing into a local disk. So it allows you to perform the deployment much faster, because you avoid to install anything. It's just cloning the OS image, so the disk image, into a local disk. But, and the pros, it's really easy to manage. It's pretty simple to understand. And so you have a consistent configuration across the cluster, as long as you're just cloning the system as expected. There is still room for configuration managers. You can install Puppet, Ansible, or whatever you are using on top of that thing. But you are still using local disk, which again is not reliable, and at the same time it could be expensive as well. So it's not easy to apply changes online. It's not easy to apply changes in the image of the system. So there's still risk of inconsistency when you play with online changes. And definitely it's not suitable for continuous integration or DevOps friendly mechanisms. So NFS root based, it's widely used, and so usually you generate the image from a golden node, or you bootstrap the RPMs or Debian packages into a folder, and then you expose this folder into the network, and you put the OS from Pixie, and that's all. That's the magic. If you want to have a read and write access, to keep some permanent data there, then there are some pitfalls. But basically it means that each node needs some kind of a breathable file system and not shared with any other nodes in the cluster. And if you have read-only, you have a potential high memory footprint. We are going to talk about that thing later. So the good, easy. You can easily apply changes online. It's easy to manage. So you have a completely consistent configuration across the cluster. So any changes that you perform in the image, it's going to be available instantly in the cluster. And there's still room for configuration managers if you are using breathable, kind of a breathable space to perform these actions. But, okay, NFS, it's a single point of failure. And as I said before, I want something really reliable, and I want to keep the wheels of the cluster going. I don't want to deal with a situation like this. In very large installations, what they are usually doing, for example, if you have a GPFS, you have a small cluster of GPFS, exporting that thing into NFS, and then apply some mechanisms to export that thing through a PXE and boot the system from PXE and so on. But again, you rely on the NFS layer, okay? Okay, so the only thing that you need to maintain, it's a small file that describes what files are eligible to write something in memory. And it's performed in this file. This is important, this is critical, because this is what it's complicating the things in the system. And so this is for read-only option, and if you have a read and write option, then you need to take care of a real complex structure, data structure, files and folders and so on, in order to work on that thing. So another option is stateless, completely stateless. So you don't have anything. You don't touch any disk at all. You just boot the system from an image. The image ends up into the memory, and it's completely reliable to any potential failure of any protocol used. So once the image in the system is in memory. And as long as you have a reliable system enough in memory-wise, so the system is going to be able to work without any drama. So you don't rely on shared file system, you don't rely on local file system. So if you have a memory failure, you have a bigger problem, right? Okay, so in order to accommodate this kind of situation, then you need to take into account that all those files that are mutable, all those files that needs to be written into the OS will take even more memory. Okay, so if your OS image takes 1 gigabyte or 2 gigabytes of data, this is the memory that you are sacrificing in favor of the cluster provisioning. And if on top of that thing you are installing an RPM package, then you need to take into account that thing in the way that you manage the cluster as well. So everything you add there, it's going to take more and more information. So pretty much I cover everything here. So usually it generates a massive RAM disk. So this is important to mention, because this is something that needs to flow through the network. So if it takes 500 megs, you're going to transfer 500 megs per node in the network. If your image is bigger and bigger, so the more information you are going to inject into the network, okay? So limited scalability when you have a single server. If you are it depends on the protocol that you are using. So, but usually, if you are using a single server at the same time, then you have a limited pipeline. Okay. So it's what is going to limit the scalability as well. So usually in these situations, the boot process takes long period of time, and that's why these solutions based on that thing tend to reduce the size of the image to the limit, to a limit that sometimes it's not even feasible for most of the users. So you could have a landing node or a login node or a build node where the user experience is going to be much more complete. And then when they try to run something in a real compute node, the experience is going to be different because they don't have all the tools available in the other nodes. So it's kind of a trade-off. And this is because you want to accelerate the boot time, okay? So this is kind of a strategy used, for example, in craze systems and so on. So you have a really light image system, and that's it. So, so the more complete is the image, the more memory footprint you will have to worry about. And there's one more thing. RAM-disk only supports 16 bits, okay? So it has some implications that probably it's out of the scope of this discussion, but it's, so for example, usernames and so on have a clear impact, okay? And so standard pipeline, it's exactly the same. So rather than booting from and cloning a disk and so on, so you boot from PXE, you load the RAM disk into memory, and then usually you have sorry, this is semi-stateless, or IBM calls it Stateless, where you have a RAM disk, traditional RAM disk, and then a portion of the OS it's in a cluster file system. So this strategy is pretty smart because this allows you to reduce quite significantly the size of the image that you need to worry about, and the majority of the files usually are in a cluster file system. And so this way you accelerate the boot time and also you reduce the memory footprint. But again, if you want to apply some changes online, so you are only able to do it on the portion of the files that are in the cluster file system, okay? And then NFS, it's still a single point of failure. Cluster file system, as long as you have mechanisms to implement hierarchy on that thing, then it's going to be more reliable. Again, RAM disk only supports 16 bits. And the mandatory, well, what it creates really painful maintenance of that thing is that it's really complex to maintain such a thing. So you need to take into account file by file, or you need to move in the small portion of the RAM disk that you want to boot with, and what files should be placed in the rest of the image that it's shared through a cluster file system. Definitely, this is not suitable for continuous integration or DevOps. So this is probably the most popular way to handle large installations, usually. So this is the next section of the talk. It's going to target this kind of requirements that we have mentioned about. So in terms of diskless provisioning, okay, so what we have done is think about a possibility to no longer use an NFS root and install a client, native client of a real cluster file system in the small init RD image, and then boot the system directly from a cluster file system. So this allows you to achieve a greater scalability. You can also support the RDMA, well, you have RDMA support and InfiniBand or OmniPath support. It's full resilient solution because it's a cluster file system, and as long as the cluster file system are reliable, then you have a reliable OS running in your compute nodes. The configuration is consistent across the cluster and small memory footprint. That's the idea, okay? Because there is no image to be fetched into the system, okay? You are running directly from a cluster file system. The consequence is that you're still, it still requires to manage this read and write tab, which contains all the files that are eligible to use to be modified in memory. So you attach kind of TMPFS on top of that thing, and then all the files that you are going to modify there that are actually expressed in this file are going to take part of memory. So it's a small memory footprint, ideally. The other bad thing is that if you need to install something that relies on a particular change in this file, there's no way. You have to restart the system, okay? So there's still room for improvement here. So I have prepared a demo. This is, so what we have is BGFS plus TMPFS and Lustre plus TMPFS. The demo that I'm going to run, it's based on BGFS and memory. So, can you read the? Is that okay? Can you bigger? Donna? Okay, so well, the thing is that what you are able to do with a system like this is that you could, well, when you run this command, it's now chroot and then the image that you are working with, that all your whole cluster is running in production. You are able to. So this is image. Sorry, I didn't mention that thing. This is image. It's read only. So the compute nodes are not able to write anything here. Whatever it's readable needs to be performed in memory. Okay. And when you run that thing, you end up into a chroot in that particular image. So whatever I type here, it's running in the image. Okay. So I can apply a change online. And once I execute this, I perform this action in this file system, it's going to be instantly available in the whole cluster. Okay. So if this is running a CentOS 7.3, and I install a package. For those that never heard about SL, it's typical user doing a mistake when they type ls, so it's kind of funny thing. Don't do that thing in production, probably. Can upset someone. So now that thing it's already available in the cluster. I can go directly to a compute node. And type SL, and this is, so it's just an example, okay? But it's the kind of a situation. So imagine something more complex, okay? Okay. I know that you love it. Okay, I will wait.
Okay, this one is
okay. Okay, so imagine a situation, and this is the other thing. So this is HTOP running in the compute node. So this is, as you can see here, I hope. So the root, it's actually a BGFS file system. And in terms of memory footprint, at this time it's 364 megabytes. It's pretty much nothing. Okay. So this is the development and testing environment that we have. And in order to recover DevOps and continuous integration, you can use that thing as an image. So you have a complete pipeline to generate the image. So you deploy the system, you generate the image, and then on top of that thing, you can apply all the DevOps-oriented methodology. And you don't need a Puppet agent in every single node. You can see its root Puppet agent inside the image. That's all. You don't need to worry about anything else. Okay, every single change that you apply in the Git is going to be performed through the to the Puppet or through the Ansible, whatever is required, and single agent. So no worries. And because you only have one instance, it scales beautifully. And there's the idea around. So here you have a kind of statistics. So when I deploy a system, so the same deployment, same system available in the compute node through deployment, deploying the system with exactly the same template, it's going to use 285 megabytes of memory. This is the memory footprint in a local file system based. With NFS root, 300. With a cluster file system, 320, 330, pretty much nothing. So you pay a price of 40 megabytes, but you gain a lot of resilience because you are using a cluster file system rather than NFS. And in order to transfer files, usually in this particular case, you need to transfer 400 megabytes per node, while if you're booting that thing, it's around 42 megabytes per node. So it's an order of magnitude of difference. And yeah, so here you have some data about the image and so on. Okay, but still, you have to restart the system if you need to perform an operation that requires to modify the RW tab. Okay? Imagine a situation where you have a complete freedom on what you want to transfer there, to modify there. So that's why I have started to look at OverlayFS. OverlayFS, it's probably you know this project because of Docker and many other processes like this. So it's a stackable file systems that expose different file systems, and then at the end another one that usually allows you to write some content in the file system. And this is completely transparent to the user. Okay, so the user experience is that this is going to be a complete file system, and you can opaque some files. So if you remove some content, some file, it's not going to be available for the user as well. So it's like the sense is that it works like a standard file system. But so this is a software developed by this guy. We have invited him to this conference. He couldn't make it this time around. Some people didn't go further in this regard because there were some bugs in the previous releases. All of them have been fixed on release. The critical ones have been fixed after 4.0 release of kernel. So all these issues regarding the IO node utilization and memory footprint are now gone. So now it's the right time to start to explore that thing again. So this is a traditional mount command line to perform that. So you have a lower here, which can be several of them. So you could stack several read-only file systems or read-only folders in in this particular moment, and then merge that thing into a single one, and then perform the operations on the merged one. Okay, so we have two strategies. One is based on SquashFS, which is native compressed image. In this particular case, it uses, we have integrated there a native cluster file system in the image. So once you boot that thing, you can access to the cluster file system. And there are two ways to deal with that thing. So you can fetch the data, you can fetch the image and use just the image in memory. And because this image is compressed and you have native access to the compressed image, so the memory footprint it's lower, it's not that high that compared to RAM disk. What you need to open the image and handle that thing through a memory. So less memory footprint. And the other way to do it is not fetching it at all because you have a reliable cluster file system underneath. So this means that you could have actually the same memory footprint that usually you have with NFS root or BCFS root or raster root. Okay. So the good thing is that you no longer need to maintain any other files, and you can apply changes online without any drama at all. And no longer need to reboot the system when you perform kind of actions like this. So, well, pretty similar pipeline. So it depends if you want to fetch the image or not. You are going to have more or less memory footprint. And then the other way around is to use similar strategy that we have seen before with BCFS or raster root file system. So you put a system with this minor small init, small kernel with a native client for the cluster file system. You mount that thing where the image is located. You, on top of that thing, mount TMPFS file system, and you merge them all into a single one, and then use you perform a pivot to the root FS, and you boot the system from there. So this way, you can achieve multiple files to allocate multiple files in the OS without any worries at all. So here we have a comparative memory footprint and data injected into the system. This is something that we are still working on that. So we are in conversations with BCFS and raster, and also with overlay developers, to achieve that. So that's why you don't have data here. But so these two options here is compared to the NFS root, as we have seen before, and traditional RAM disk with a complete OS. In this case, it takes the 1 gigabyte and a half pretty much, plus the memory required to run the OS. So it takes, in this case, 2 gigabytes of data, 2 gigabytes of memory. So it's quite a large, when you have 1 or 2 gigabytes per core in many cases. And then the data transfer is quite high, so it's quite significant. And then if you are using overlay FS on SquashFS with fetching, this means that you are getting the image and you are running the OS from this image, because the image is compressed. So this is the memory footprint. It's less than a half. It's pretty much 3 times this value. So it's, in terms of automation, it's really high. And then you need to transfer 555 megabytes of data into the network, which is still reasonable because what you are getting out of it, it's kind of a really large and complete system. Okay, but there's another way to do it. If you are using a cluster file system underneath, and you rely on this cluster file system, you don't need to fetch even this image. Then the memory footprint is rather low, so it's pretty similar to what you have here. So you pay a maybe slightly higher price, but it's still reasonable. And then the other thing is that in terms of data transfer into a network, because of booting the system, it's 58 megabytes, which is pretty much nothing. Then, if you do the math, you will be able to see that you can still use a gigabit Ethernet for provisioning a reasonable size cluster. If you want to go way further, just use InfiniBand or OmniPath, and not a big deal, as long as you are using kind of these technologies. So as a conclusions, well, regarding diskless provisioning, as we have seen, so we have simplified quite a lot of administration. We have improved the reliability of the system and reduced quite significantly the memory footprint of the system. So we're talking about with a minor increase of around 35 megabytes, we have gained a lot in back. And then we have also improved the scalability. So the same cluster file system that's able to cope really high I/O demanding jobs, it's going to be able to handle that thing. And then in terms of improvements achieved with the current implementation of overlay FS using Squash FS in this particular case, so we have been able to reduce significantly the memory footprint. So we are talking about this reduction from rather than 2 gig to 750 megabytes. We have been able to include a native cluster file system client natively, and this means that so we get really large scalability, or potentially a really large and nice scalability. What else? So if you don't fetch the image, then the memory footprint it's pretty much negligible. It's pretty much nothing. And then because of the overlay FS and this file system layers, it opens a bunch of new opportunities and new strategies that you can apply on top of that thing. So Carlos Fena is going to talk tomorrow about UnionFS, so CERN BMFS, which is based on UnionFS.
No, not tomorrow.
Not tomorrow?
Yes, now. Yes, now.
Okay, I'm confused. So it's, sorry. So similar kind of technology, or maybe it's even compatible with that thing, because overlay FS allows you to handle other stackable file systems as well. So imagine a situation where you want to boot bare metal, and you want to accommodate a user requirement to have completely isolated image, and also applications, and also data sets to work with. You could be able to achieve that thing with the same technology. So it's just a matter of putting this, injecting these stages there, and to enable these different layers in the same overlay FS. So that's all I have. Thank you.
I think that in order to be on time, as we're going later to do this roundtable about this provisioning file systems, we can keep the questions for later on with all the opponents, okay? So, Carles. In the meanwhile, if Carl is preparing, if you want to do some question, quick one. Microphone. You have a question, you have to prepare your talk. And you are going to discuss later on in the panel.